In this tutorial, we will be discussing the heated curve for water. Delta H of vaporization, or delta H vape, is the amount of energy, which is abbreviated with a Q, required to vaporize 1 mole of a liquid. Heat is required at constant pressure to vaporize the liquid to a gas. In other words, you have to put energy in, which is making it endothermic. It's somewhat temperature dependent. Because it's endothermic and you're putting energy in, delta H of vaporization is positive. It's referred to as either the heat of vaporization or the enthalpy of vaporization. Now, condensation is the opposite of vaporization. So if vaporization is always going to be positive, the opposite would be for condensation. So the condensation will be a negative value. As the liquid is heated, its temperature increases linearly until it reaches the boiling point. So the heat is added and the temperature increases. C is the specific heat that you most likely learned before. It's the amount of energy required to raise the temperature 1 degree Celsius for every gram. So it's joules per gram degree Celsius. So if we have a specific mass here and we're going to try to raise it a temperature, it's the change of temperature, the amount that you're raising the temperature, times the mass times the specific heat, and that'll give you the amount of energy that it took to do this. At the boiling point, notice it levels off here. All the added heat goes into the boiling of the liquid. The temperature therefore stays the same. Once all the liquid has turned into a gas, the temperature can again start to rise, which is why the line is going up once again. So let's take a molecular view of this. As a solid, and it's warming up, the molecules are moving faster and faster and faster until it gets from being a solid up to the melting point, however cold it is to begin with. Once it starts to melt, the molecules start to break apart. There's no actual temperature difference while this is happening. And then the molecules, once it's all broken apart, the temperature will start to rise again. And this is the liquid warming up. And then once again it will level off into stage 4, where the molecules start to escape. This is when it's boiling. The molecules are going from a liquid to a gas. And once all of them are into a gas phase, the molecules will start moving faster and faster and faster as they get warmer and warmer. This is taking the temperature of water, H2O, from -25 up to 125. Let's see how that looks in calculations. Let's say we have 1 mole of ice, which is H2O. We're trying to get it to go from -25 to up to 125. Each one of these line segments have to be done individually. So we can start by going from -25 to the boiling point of 0. So the first step is to go -25 to 0. Well, 0, the final, minus the initial, so 0 minus -25 is equal to +25. 1 mole of ice is H2O. If we look on the periodic table, we know there's 2 times 1.01 and 1 times 16.00. That combined is approximately 18.0 grams. That's where they got this mass from. And then the specific heat is a known quantity. So we can do Q is equal to mass times the specific heat times the change in temperature, which means 18.0 grams times the specific heat of 2.09 joules per grams times degrees Celsius times 25 as the change in temperature. We multiply all that together, and that comes out to be 941 joules of energy that needs to be added to those 18 grams to raise it 25 degrees Celsius. If we wanted to put it into kilojoules, 0.941. Now we're on to segment 2. In segment 2, we now have it in 0 degrees, and we're making it melt. So that's the amount of moles times the delta H of fusion. We're still dealing with 1 mole of ice. The delta H of fusion is 6.02 times kilojoules, 6.02 kilojoules per mole. So that's going to be 1.00 moles times 6.02 kilojoules per mole. That comes out to be 6.02 kilojoules. Now we are right here on our curve. Before we get to 125, we have to get up to the point where it boils. So we're going from 0 to 100 to the boiling point. So once again, we have 1 mole, which is equal to 18 grams because of the molar mass, going from 0 to 100. So that's 100 minus 0. Change of temperature is 100 degrees. The specific heat is 4.184, which is a known. So Q is equal to the mass, 18.0 grams, times 4.184, the specific heat, times 100 degrees Celsius. Multiply that all together, and that comes out to be 7.52 times 10 to the third joules, or 7.52 kilojoules. Now we are right here on the graph. We're at the boiling point, and we have to wait for it all to boil to turn into gas, and that's the heat of vaporization. This should say 40.7 on your notes. Q is equal to N times the delta H of vaporization, which means, since we're still dealing with 1 mole, 1.00 mole, times the heat of vaporization, which is 40.7. We're going to multiply those out to be 40.7 kilojoules. Finally, we're at the steam part. We're going from 100 degrees Celsius up to 125. All the particles are now gas, and they can be heated up again. We're still dealing with 1 mole, so the molar mass is 18 grams, so 1 times 18 grams per mole. The specific heat is 2.01 joules per mole, that's a known, and we're going from 100, decimals in the wrong place, the 100 to 125, so final minus initial is 25 degrees Celsius. So the Q is equal to 18.0 grams times 2.01 joules per mole degrees Celsius times 25.0 degrees Celsius. The heat comes out to be 904 joules, or 0.904 kilojoules. Now, in order to figure out the amount of energy it takes to go from negative 25 all the way up to 125, we have to add all these segments together, which means we're going to add 0.941 plus 6.02 I'm doing it all in kilojoules, make sure they're all in the same unit, plus 7.52 plus 40.7 plus 0.904. That comes out to be 56.085 kilojoules. Looking at significant figures, this one goes out to the hundredths place, this one goes out to the tenths place, so it's going to be 56.1 kilojoules. And that's how you use the heating curve.